In the 1950s, as electrification extended to rural areas, AC electrification, which could reduce construction costs, became essential, and there were high expectations for AC vehicles. Even if investment in ground facilities decreased, the benefits couldn't be realized if the vehicles remained expensive. Therefore, various attempts were made to develop a simple drive system. The KuMoYa 791 adopted AC commutator motors, which did not require complex and cumbersome onboard rectifiers. Additionally, the KuMoYa 492 and 493, compatible with both AC and DC sections, were developed and tested. On the other hand, the advancements in silicon rectifiers had the potential to make the onboard rectifier system advantageous and were the most promising technology at the time. However, all these systems required commutator motors. As long as contact wear components like brushes and commutators were necessary, maintaining multiple motors in EMUs was challenging. The ideal solution would be a motor without wear parts except for bearings. There exists a dreamlike motor that uses electromagnetic induction to conduct current to the rotor without contact, magnetizing the rotor to generate power. This is the induction motor. However, the induction motor is troublesome when it comes to changing rotational speed, and even getting it to start is no straightforward task. To induce electromagnetic induction, a changing magnetic field is required, and to generate rotational force, a rotating magnetic field around the rotor must be created. With three-phase AC, which has a 120-degree phase shift, creating a rotating magnetic field is straightforward. However, three-phase AC electrification requires two overhead wires, making the infrastructure cumbersome and diminishing the benefits of AC electrification. Single-phase AC, like DC electrification, requires only one overhead wire, but single-phase AC alone cannot create a rotating magnetic field. To run an induction motor on single-phase AC, a capacitor must be used to supply phase-shifted current to the auxiliary winding, or a starting motor must be used to accelerate it. The complications with single-phase AC induction motors don't end with starting them. Since the rotational speed depends on the power supply frequency, it was not easy to change it with the technology at that time. Using the capacitor starting method, if the capacitor remains connected, it behaves similarly to a three-phase AC induction motor. Voltage control allows for torque control, making it possible to adjust the rotational speed if there is a load on the output shaft. However, its torque characteristics are worse than those of a diesel engine. Running an induction motor at speeds far from synchronous speed is akin to controlling the speed of a manual transmission car using a slipping clutch. The low-speed high torque required for vehicles is unattainable, making it unsuitable for vehicle use. Additionally, keeping current flowing through a connected capacitor leads to its degradation over time. Despite these challenges, engineers endeavored to make the single-phase AC induction motor workable for vehicles. This was the background for the creation of the KuMoYa 790, one of the most unique and unconventional trains in JNR's history. How to operate a vehicle with a motor that cannot change rotational speed? It was not feasible to let it slip continuously, like a friction clutch. This led to the adoption of the hydraulic transmission familiar in diesel vehicles, but it was not possible to connect it directly to the motor running at a constant speed via a clutch. Thus, they utilized one of the hydraulic transmission's strengths, incorporating a clutch function through the use of oil. This is the same charge-discharge oil mechanism known from the DD51 and KuMoYa 181 series. It's not feasible to equip the motor and hydraulic transmission as a set in the bogies like conventional EMUs. Instead, like diesel cars, the drive unit was mounted under the floor, extending the propulsion shaft to drive the bogie axles. As a prototype, the main motor was compact at 130 kilowatts and used a bow collector instead of a pantograph for current collection. Another interesting mechanism similar to diesel cars was incorporated. As mentioned earlier, starting the motor could be done using a capacitor and starting winding or a dedicated starting motor. The KuMoYa 790 adopted the latter, effectively making the EMU have a structure akin to having a starter motor. The 10 kilowatt starting motor was constantly connected to the main motor. Next to the starting motor was the main transformer. Despite the usual concern of heavy transformers in AC systems, it was compact due to the low output. The main motor was directly connected to the input shaft of the hydraulic transmission. Operating at a low speed of 1470 RPM, it did not have a speed increase mechanism. Adjacent to the hydraulic transmission were accumulator units for charging and discharging oil under pressure. The output shaft of the hydraulic transmission connected to the reversing gear via the propulsion shaft, driving a single axle. The starting motor itself is initiated with the help of a capacitor and reaches 1000 RPM in about 7 seconds. At this point, a centrifugal switch disconnects the capacitor from the circuit. Simultaneously, the main motor is powered, and both accelerate together without the capacitor, reaching around 1500 RPM in just 1 second, near synchronous speed. This state is akin to idling in diesel vehicles. Even at maximum output, the main motor continues to run at almost the same speed. In the idle state, due to the counter-electromotive force of the motor itself, very little current flows, resulting in minimal losses compared to a diesel engine. Since the starting motor was already turning, its power was also used during travel, contributing an additional 6 kilowatts. Once the motor starts, the vehicle is ready to depart. To transmit power to the propulsion shaft, oil is injected into the hydraulic transmission. As the oil in the transmission increases, torque is gradually transmitted, enabling smooth starts despite the constant speed of the main motor. The master controller operation involves turning from the cutoff position to the start position to activate the main motor, and then moving to the first notch to begin oil injection. The tractive effort gradually increases as shown in this diagram, and once it surpasses rolling resistance, the vehicle starts, aligning closer to the inherent torque characteristics of the transmission. Unlike previous EMUs, there is no jolt during startup, providing an ideal startup characteristic without any additional operations, enhancing ride comfort. The power notches extend to the second notch, where oil pressure inside the hydraulic transmission increases to 4 atmospheres, strengthening the transmitted torque. When a force from the wheels tries to spin the main motor on a downhill, it exceeds the synchronous speed, turning the motor into a generator. Because of the hydraulic transmission, the main motor doesn't exceed synchronous speed, generating at almost the same frequency as the power supply. This AC power can conveniently be fed back through the transformer and returned to the overhead lines. This simple yet effective system excited engineers, given its simplicity, compared to modern regenerative braking circuits. However, relying on hydraulic transmissions introduced challenging issues. As the characteristic curve indicates, the controllable speed range was narrow, and using the inefficient hydraulic transmission resulted in even worse power efficiency than resistor-controlled DC EMUs. Hitachi improved the hydraulic transmission by altering the angle of the guide vanes to change the oil flow direction, reducing torque drop at higher speeds. They also plan to release the guide vanes at certain speeds, allowing them to rotate freely and transform the hydraulic transmission into a fluid coupling. With a fluid coupling, the output and input shaft speeds are closer, allowing efficient power transmission if the motor speed stays near synchronous speed. This unconventional hydraulic EMU added complex mechanical control mechanisms to simplify the electrical system, diminishing its advantages. The increased capacity and lower cost of silicon rectifiers outperformed the cumbersome mercury rectifiers, and despite the issues with commutators and brushes, the direction moved towards using conventional DC motors.